Have you ever wondered how the massive freight train cars that move millions of tons every single day are built? In every journey, they face extreme heat, freezing temperatures, enormous weight, and thousands of miles without stopping for a moment. But what really happens inside the giant metalworking facilities where these steel giants are born? Freight train cars are a symbol of heavy industry. Behind them, there is a world of engineering, welding, and quality control that few people ever see. Inside these metal workshops, raw steel is transformed into structures capable of supporting extreme loads without failure. Every detail is engineered to ensure that rail transport remains one of the most efficient ways to move goods across the planet. The rail industry has quietly expanded, connecting ports, factories, and farming regions. What looks simple at first glance is actually the result of a highly complex industrial production system. Here, technology and skilled labor work side by side to create equipment built to last for decades, facing tough weather and time itself. Today, we are stepping into one of these factories to follow every stage of how freight train cars are made. From raw steel to the final finish, you will see how engineering turns tons of metal into precision and movement. If you enjoy factory videos and want to understand how things are truly made, subscribe now and join me on this journey. Everything begins with steel. It arrives in large blocks and coils that go through rigorous quality checks before entering production. Inside the shop floor, the material is weighed, labeled, and separated according to thickness and composition. This is the starting point for structures that will support dozens of tons in constant motion. From there, the steel moves to cutting and shaping areas. High-precision equipment cuts each sheet to exact dimensions. Following detailed engineering plans, each piece will become part of the chassis, the sides, or the floor of the rail car. Production is monitored in real time to ensure the steel keeps its correct thickness and shape for the next stages. Then, the sheets are heated and formed to achieve the right curvature and rigidity. Industrial furnaces bring the steel to extremely high temperatures, and hydraulic presses apply the force needed to shape the main structures. The balance between heat and pressure is essential to turn raw steel into strong, reliable components. The result is a solid and precise base. Every piece leaves this stage with markings that guide its future assembly. It is just the beginning of a process with hundreds of steps that demand technical coordination in every detail. But for this steel to survive changes in weight, temperature, and long-distance vibrations, it still needs a special treatment that comes next. The strength of a freight car begins long before cutting the sheets. It starts with the choice of alloy. In these workshops, regular steel receives controlled amounts of carbon, manganese, and nickel. Each element plays a role. Carbon increases hardness. Manganese improves impact resistance. Nickel stabilizes the metal against extreme temperature changes. This combination is what gives the material real durability. Manufacturing follows strict mechanical engineering standards. After melting, samples are taken and tested for tension, impact, and fatigue resistance. The goal is to detect any deviation that could weaken the structure. If approved, the steel goes into the rolling stage, where it is stretched into uniform sheets. Every millimeter is checked to ensure it meets exact railway specifications. During rolling, the steel is reheated and compressed between industrial rollers until it reaches the precise thickness. This increases density and eliminates internal air pockets, ensuring it can support loads beyond 100 tons. Temperature and pressure are fully automated, and every variation is recorded. Everything is designed to guarantee safety and consistency. Once cooled, the steel goes through thermal normalization to stabilize it and prevent future deformation. The final result is an alloy ready to endure rain, heat, freezing cold, and long journeys on steel rails. This is the moment when ordinary steel becomes a high-performance material prepared to move industries around the world. After approval, the most visual stage begins. Huge steel sheets are placed on cutting platforms with millimeter-level accuracy. Each sheet is cut according to technical drawings, defining the exact size of the sides, floor, and chassis. Here is where the railcar begins to take shape, turning raw blocks into structural components. Next comes forming. Hydraulic presses add curves and reinforcement where needed. Temperature and pressure are calculated so the steel stays strong without becoming brittle. This balance ensures the car can handle shocks, vibrations, and heavy shifting loads during rail transport. Technicians constantly check thickness, alignment, and edge quality. Any flaw is corrected immediately because even small errors affect future assembly. Advanced measuring systems track every step to guarantee uniformity on a massive scale. By the end of this phase, the steel sheets have become recognizable railcar parts. The foundations are ready to be joined into a single structure. But before that can happen, the steel needs one more crucial step: welding. With the steel cut and shaped, the factory moves to the process that turns individual parts into one solid frame. Every weld is done with precision to ensure long-term strength. The heat is calibrated to fuse pieces without damaging the steel. Each joint follows strict engineering standards. During welding, the pieces are held in place by metal fixtures that guarantee perfect alignment. Experienced technicians monitor heat and welding speed to create a uniform bond capable of withstanding constant stress and impacts. After each stage, the structure cools naturally to prevent warping. When the main welds are complete, inspections begin. Ultrasonic tools and liquid penetration testing detect internal flaws. Any irregularity is immediately repaired. This careful inspection ensures each railcar meets strict durability and safety standards. At this point, separate steel pieces have become a single backbone. The welded frame is now ready to receive axles, suspension systems, and reinforced supports. The assembly is moving toward the mechanical heart of the train car. With welding complete, the railcar's frame takes shape. Side panels, the floor and the chassis are positioned and joined into the central body. Massive factory cranes move multi-ton pieces with precision. Alignment is checked repeatedly to guarantee long-term stability. Technicians reinforce critical points with additional welding and metal fasteners. These reinforcements help the structure withstand constant load shifts and heavy impacts on the tracks. Every section is installed according to strict engineering plans. Cross braces and support beams are added to increase rigidity. The frame now reaches its full dimensions and resembles a real freight railcar. The interior is still empty, but the structure already shows its true scale and strength. Measurements are taken again and again to ensure there are no twists or misalignments. Once approved, the frame is ready to receive the systems that bring movement to the railcar. Axles, wheels, and suspension components wait nearby, prepared to turn this steel structure into a machine capable of crossing continents. The railcar only truly comes to life when it receives its axles and wheels. These components are made from high-density steel and go through an advanced precision machining process. Each wheel is molded, turned, and balanced to support up to 20 tons of weight. Even the smallest imperfection can affect performance and lead to early wear on the tracks, so specialized equipment measures every detail with accuracy. The axles are assembled in pairs, forming what engineers call bogies. These sets carry the full weight of the railcar and provide stability during curves. Assembly follows a controlled sequence. First the bearings, then the axles, followed by springs and shock absorbers. This suspension system absorbs impacts and keeps constant contact between wheels and rails, reducing friction and extending the railcar's lifespan. After assembly, each bogie is tested on platforms that simulate real track movement. Sensors monitor vibration, temperature, and structural resistance. Only units that meet strict safety standards move forward to final installation. This quality control ensures the railcar can travel long distances carrying minerals, grains, and fuel without structural failure. Once the bogies are installed, the railcar can support itself and move inside the factory. But before it heads to full rolling tests, it needs one more crucial component: the system that allows dozens of tons to stop safely. No railcar is complete without its braking system, the mechanism responsible for controlling massive weight in motion. Inside the industrial shop, each structure receives a network of valves, cylinders, and tubes that form a compressed air circuit. This air runs through the entire train and activates in sync, ensuring every railcar slows down at the same time, even in long freight compositions. Assembly begins with air reservoirs, followed by compressors and main lines. Every connection is checked to prevent leaks and to maintain consistent pressure. Technicians adjust the system calibration and measure brake response time, testing how quickly the railcar stops after activation. Precision is essential since any failure can compromise the entire freight operation. After installation, the system goes through full load braking simulations. Sensors record component temperature, friction force, and wheel behavior during deceleration. These tests mimic real situations like steep inclines and long curves. Only after passing all evaluations does the railcar move to the finishing stage. With the braking system approved, the steel structure becomes a safe and reliable machine. Every valve and tube is the result of precise calculations and specialized labor. Now the railcar is ready for the final protection that ensures long-term durability. With the structure complete, the railcar moves to finishing. The goal here is to protect the steel against corrosion, strong sunlight, and humidity. It starts with a deep cleaning where the entire surface is blasted with fine abrasives, removing impurities and creating texture for adhesion. Then, a special primer coat is applied as the base layer. Next comes industrial painting. High-resistance coatings are sprayed in multiple layers, forming a thick barrier against rust and wear. The application happens in controlled environments where temperature and humidity stay within specific limits, ensuring a uniform and long-lasting finish. Even after years of exposure and constant contact with dust and debris, the protection remains. Each railcar receives more than 100 liters of paint. Colors vary depending on cargo type and operating company. but the purpose is the same: extend useful life and simplify maintenance. After painting, the railcar enters a curing chamber where the surface hardens and gains shine and impact resistance. When it leaves the paint booth, the railcar looks ready, but it still needs one more challenge: extreme loading tests to prove its real-world strength. Before leaving the factory, every railcar faces tests that reproduce the harshest rail conditions. Industrial machines apply pressure to the chassis and sides, simulating real cargo loads. Sensors measure deformation, vibration, and internal stress, verifying whether the steel, welds, and axles can endure constant force without failure. During testing, the railcar also faces controlled impacts and rapid temperature changes. The goal is to confirm resistance in environments ranging from freezing climates to intense heat. Every measurement is compared to international railway engineering standards. Only models that pass all criteria move to final inspection. Stability tests follow. The railcar rolls on a test track at different speeds, while technicians monitor suspension behavior, wheel grip, and braking efficiency. This stage confirms that the system performs as designed and that cargo will travel safely and smoothly over long distances. After all tests, a performance report is logged and the railcar receives its official serial number. Now fully certified, it moves to the final stage, preparing for delivery to the railway companies. With testing complete, the railcar enters the shipping area. Here, it receives final adjustments such as identification tags, coupling systems, and communication connections. Then it rolls onto internal tracks leading to loading yards. Transport is done in long lines of brand new railcars ready to join national freight fleets. These railcars are designed to carry minerals, grains, fuel, and shipping containers. Each type has its own features, like reinforced lids or side-loading doors. This versatility allows modern rail logistics to supply ports, industries, and farmland efficiently. Factories also maintain maintenance teams to ensure each unit remains safe for decades. Industrial technology evolves every year, introducing new alloys, remote monitoring systems, and more precise welding techniques. The goal is to make rail transport increasingly efficient and environmentally friendly. When a railcar leaves the factory, it carries more than cargo. It carries the result of thousands of hours of engineering, planning, and testing. Steel that once entered the furnace raw now travels across continents, connecting markets and powering economies. And as one railcar begins its journey across the country, new ones are already in production, continuing the legacy of an industry that keeps the world moving. From raw steel to a railcar ready to cross the nation, every step of this process shows how essential industrial engineering is for modern logistics. Inside these factories, thousands of parts become structures capable of supporting entire economies. Every weld, every axle, and every test ensures these metal giants operate for decades. These railcars do more than transport goods. They move energy, food, and raw materials. They help cities grow, connect regions, and support global commerce. Steel once poured into a furnace becomes motion and efficiency that millions rely on. With the advance of industrial technology, new production methods are making this process more efficient and sustainable. Digital control, new alloys, and monitoring systems are reshaping rail engineering. Each new railcar becomes lighter, stronger, and more efficient than the last. Now tell me in the comments, did you imagine all this work behind a single freight railcar? If you enjoy learning how things are made and want to explore more industrial stories with me, like the video, subscribe to the channel and turn on notifications. There are many more incredible stories inside the factories that keep the world running.